Yo guys, Dim here. Today I'm going to be making a sort of brief video about the basics of electronics if you're going to add additional accessories to your e-bike. This also goes for e-scooters or really any lithium-ion battery powered device, as long as you can tap into that battery. So the first thing I want to go over is how we're going to actually power the system. Most lithium-ion batteries run 72 volt, 48 volt, 32 volt, and then most electronic accessories for like moving vehicles are 12 volts because they run off of a 12 volt battery. You want to be able to take that 72 volt source and convert it down to a 12 volt source. That's what a step down converter is for. As you can see on this one, the input is between 18 and 90 volts and the output is 12 volts, 25 amps max. If you use a lower input voltage, this maximum output amperage goes down as well. You need to consult with the documentation to figure out for your voltage range what amps you're going to be able to get. So the first thing I want to do is hook this thing up to my battery. Here's my battery pack. This is a 72 volt battery pack I built. This is the part where I joined the battery negative terminal with the output negative terminal of this Anderson connector. So I'm going to remove this tape. And as you can see, there are two ring terminals right there. I'm going to remove this nut. Now I'm going to add this ring terminal to it, put the nut back on. And I almost made a mistake here. I totally forgot. If we look closely at the diagram, this red and black wire is actually the input. These would be the output. So I'm doing it wrong. I got to use this connector here. Here I've already made a connector for it. You have the two ring terminals here. And then on this side you have the male waterproof connector. Actually, this is the female waterproof connector. And that's what's going to connect to this, so that you can always disconnect the transformer. Get it nice and snug, and we're going to wrap it in electrical tape again. We're going to do the same thing for the red side. And we're just getting the red wire from this connector. And we do the same thing, we wrap this in electrical tape. So this part of the process is going to vary from person to person. It really depends on what your battery is like and what your system is like. But you just need to find the point where you can get a 72 volt source from the battery. In this case, I made that accessible via this waterproof connector. And from here on out, the rest of the system is going to be the exact same across everybody's bikes, whatever. The only part that's going to be different, like I said, is getting that 72 volt source. Just a little finishing touch here. I'm going to bring that out through this port. Great. So now this is the main power going to the speed controller, and this is what we're going to use for our accessories. So now that we have that, I want to plug this into the converter, and then I want to check the voltage of these two wires to see if we are in fact getting 12 volts DC. Here I have a multimeter. It's a pretty cheap one. As you can see, that's the sign. This is the symbol for DC voltage right here. This is the sign for AC voltage right here. We're not going to use AC. So let's go here and let's put it on 20 because we're looking for 12 volts DC. Plugging that into there, let's grab the red lead, touch it to this red ring terminal, and the black, and touch it to there. And as you can see on the meter, we have 12 volts. Disclaimer, don't touch these two together. That'll cause a short. It might kill the converter. Don't do it. So this is basics. The first concept I want to introduce you to is a switch. This is a very basic switch. This is what you see in most houses. This one's rated for AC voltage only. But the idea is that you have these two terminals here. When the switch is in the off position, which is down, these two terminals have no continuity between each other. There's something in there that's open. And then when the switch is up, these two are physically touching each other through an internal mechanism that's touching two contacts. The way that switches work in houses is that they're rated for pretty high amps. As you can see, this one's rated for 15 amps. And what you'll do with a house switch is that you'll have the power coming from somewhere in the house. It could be from the panel, it could be from a box. It'll go to one of these, and then the other one here would be connected directly to the light. And then from the light, it'll be connected back to ground. This would be interrupting the flow of current. This is the most basic kind of switch because it's rated for very high amps. So you could just put whatever you want after it as long as it doesn't exceed 15 amps. Now, the problem we encounter with little switches like this one, and this is what happens in a car, in a bike, in anything, is that these switches here will not take more than a couple milliamps because they use very thin wires and contacts on the inside. These are not rated to have loads placed after them. These are just switches that you look for continuity in and then power up a relay. And I'll explain what a relay is. But all you need to know is do not wire this the same way you would wire, say, a house switch, because that'll burn up this thing. Let me grab a switch that's rated for DC and I'll show you an example. So here's an actual switch that's rated for DC. So this switch as well only says 15 amps to 50 volts AC. But I've used it before with 12 volts DC and it worked just fine, so I'm going to use it. This can handle up to 15 amps, so just like the house light switch here, you can put a load after it as long as it doesn't exceed 15 amps. And just to clarify, when I say load, I mean virtually anything. It could be a light, it could be a horn, it could be a fan, it could be anything that draws amps. Here's a bunch of jumper cables. And before I even use the switch, I'm just going to show you how you would power a light. Here I have a light that I plan on mounting on this bike, and it uses a male waterproof connector. Here I have a female waterproof connector, so I'm going to attach that. And let's just mount it to my handlebar here. Alright, so now it's decently mounted on there. Now let's suppose we just wanted our bike to power this light, so that when this converter is connected, the light is on. What we would do is we would connect this red to our light. And I'm pretty sure I reversed the polarity here, so black is actually going to be where the positive side of the light is connected to. In your case, it's probably going to be red to red, black to black, but I got this mixed up. These connectors that I'm using that are already pre-crimped use red as the first one, whereas this light uses the left as the negative. So it's just colors, but you know, pay attention to them. So now let's also connect that black to what is the light's negative. And with some luck, if we connect this, we should get the light to turn on. As you can see, the light's on. And let's say we wanted to turn the light off. Well, we could just disconnect this alligator clip and the light turns off. And when we reconnect it, the light turns on. And so that works. And it does provide light. But let's say you didn't want it to be controlled by this alligator clip. You wanted a switch to be able to do what we're doing here, which is manually breaking the circuit, closing the circuit. That's when a switch would come in, something like this. So let's go ahead and disconnect the power. And now let's take that alligator clip that we were just manually moving, and let's put it on one side of this switch. And let's grab another alligator clip. And let's put it there, which is where we were connecting this to previously. And connect it to the other side of the switch. So now we have a switch, and make sure none of these are touching. I'm just demonstrating here, but you wouldn't actually use alligator clips. You would want to use some Y connectors here, and then screw down the terminal. I'm going to make a second part to this video, which is going to be a little more advanced, and there you'll see the proper way to make connections in a way that they won't come loose while you're riding around with all that vibration. So now let's go ahead and connect this again. As you can see, the light is on, and if we flick this switch, the light turns off. That's cool. And that works. And if you're using switches that have like a high amp rating, you could do this. You could just directly connect to the light, as long as that's what the switch is rated for. The problem is, when you're dealing with smaller switches, such as this one, which has many switches in one, this is not supposed to have even more than 1 amp going through it. So something like this light, which draws 3 amps, would most likely burn up this switch. And so in order to protect our switch, we are basically going to use something called a relay. And this is a relay. This isn't the one that we're going to be using. This is one that you would typically find in a controls panel. You wouldn't find this in a car. It has a lot of terminals for multiple throws, multiple pulls. That doesn't matter. But the reason I'm bringing this one out is because it's transparent, so you can actually see inside and see what's happening on the inside. High-level overview, what a relay is a switch that is controlled by electronics. So instead of the switch like this one, which is controlled by a human that makes it go up and down and is physically closing something in there with our human strength, this here has a coil, and that coil generates a magnetic field. And then when that magnetic field is active, there's another magnet in here that gets pulled in and closes the two pads right here. If you could see that, I know it's a little hard to see. So on the left side, that's a normally closed position, so that when there's no power going through that coil, it's always touching that pad. But then when there's power going through that coil, you're going to see that this thing in the middle is going to flip over and touch the right side, and that's what closes the circuit. If we look at the little diagram here, we could see that the bottom, this is the negative, this is the positive, this is what controls the relay. I'm not actually going to be able to show you this relay in action because the coil is to be powered by a 24 volt AC source and not a 12 volt DC source like we have here. But this is just for demonstration purposes. The actual relay that I'm going to be using is this one here, which is rated for 12 volts DC. As you can see, it handles 30 plus amps. So I'm not going to be able to show you the actual closing on the inside of this relay, but you will hear a click when the relay closes. So let's go ahead and power the coil. So if you look at this tiny little diagram here, from 85 to 86, that's where the coil lies. On the back here, we could see an 86 and an 85. So let's power that up with 12 volts DC. And with a coil, the direction of the current doesn't matter. So when we hook this up, we'll hear a click in that. You heard that click? Let me go ahead and remove this. So that's the relay physically closing inside. So let's close it. And so now while the circuit inside is closed, that means that between 30 and 87, there should be continuity. This little diagram here, what it's telling us is that 30 is the common. And when there's no power to the coil, it's connected to 87A. But when there is power to the coil, this flips over and connects to 87. So that's your normally closed side, and that's your normally open side. For most purposes, you'll only use the normally open side, because what you want is that when you hit a switch, the circuit closes and then it powers something. But in some cases, you want to use the normally closed side. The normally closed side is so that when a switch is off, this does something. So let's go ahead and check continuity between 30 and 87. So 30 is this one on the bottom, 87 is this one on the top. Put the meter in continuity mode, and you hear the beep. When we touch that and we touch that, we get a beep. And then if we touch the middle one, which is the normally closed one, there's no beep. That's because it's now open. However, if we disconnect one of these power, so now the coil in there is no longer powered. When I touch between here and the normally closed side, we get continuity. Between here and the normally open side, there's no more continuity. So that's pretty much what a relay is. It's just a switch, except instead of flicking it by hand, there's a magnetic coil in here that flicks that switch. Moves it from 30 to 87. In the normally closed position, you're on the left, 87A. That's when the coil is off. It's always touching 87A. In the normally open position, when the coil is powered, it's touching 87 and not touching 87A. So that flicks between 87A and 87 when you power this coil. So I hope that makes sense. If you don't fully understand yet what a relay is, go look at another video, get a couple more examples. I know a really good video on relays. I'll link that in the description as well. If you understand what a relay is, you could pretty much figure the rest out. Now, let's suppose we wanted one of these buttons here, say this light button at the top here. Let's say we wanted that to power this. Like I said before, this is a very small button. This whole thing uses very small contacts. If you try to power the light directly from this, and you can look at the documentation and check how many amps this would handle, you would burn this up. It would kill this if you tried powering the light directly from it. If you had this positive source running to the common of this, and then this switch connected to the light, and then the light connected to the negative, you would kill this. So here are the pins coming out of this. Don't worry about this little connector. I don't even know which one does this. So I'm going to show you, if you don't know which switch corresponds with which wire, how you can figure that out. So what I do know is that black is common, and it's almost always common. So black, you can rely on that being common. If it's not, you just got to brute force all the possibilities, but I'll show you. So we have this switch on, we have this one off, this is off, this is just a momentary switch, and this is in the middle position, so the left and right turn indicator are off. And we have the meter still in continuity mode. Now, let's put one end of the meter to this common wire, and let's try out all these different wires over here. It might be this one. Let's just verify by touching the other ones. It's not that one. It's not that one. And it's not that one. Okay, so purple. Let's go ahead and touch that. And let's touch the switch off. Okay, so we're going to look at black and purple only. These other colors here, they respond with the rest of the switches on here, the left turn signal, right turn signal, and the horn button, and the hazards just closes the left turn signal and right turn signal at the same time. But let's just look at black and purple. So our goal is we want to power this light using this switch right here. So we want to use a relay to do that so as not to burn up this switch. So the relay is going to be connected after this switch. So let's go ahead and get a positive power source going from here to this purple, and make sure we disconnect this. So we're connecting this from the positive of the converter to the purple of this switch, and then we're going to connect this black side to the relay. So we know that the relay is 85 and 86, which is this, 86, 85. So let's go ahead and connect this to either one, 86 or 85. And then let's connect the other side of this to this black terminal at the converter to close that circuit. So now, let's just go ahead and power it up. Let's turn this off. When we hit this switch, we should hear this click. It's kind of hard to tell unless if you hit this one hard, all you hear is that, but if you listen closely, you can hear the relay turning off and on. So we know that's good. So let's go ahead and disconnect that once again. And we already figured out that 87 is the normally open side. So we're going to connect 87 and 30. So what we're going to do now is we're going to take another jumper cable, and we're also going to power this from the converter. So this converter is powering multiple things. This is called parallel. We're wiring things in parallel. And we're going to connect that here to this common side. Let's go ahead and take this normally closed side. Let's take this normally open terminal, connect to that, and then let's connect over here to the light. And like I said, I reversed the polarity on this, so we're going to do the black side. And finally, to close the circuit, because now we have the power, it's going to the switch inside the relay, and then it's going to the light, and now we have to go back to ground, which is our black terminal here. You know, make sure none of these are touching where you don't want them to touch. Like if this touched this, that could be really bad. That would short circuit. That's why you got to be very careful when you're doing it like the way I'm doing it, just haphazardly. And you want to use proper terminals that are insulated so nothing can potentially touch anything else. But anyway, it looks like everything is hooked up, and we already verified that the relay comes on when we press that switch. If we connect this, and let's turn it off first. At first, nothing happens, but if we hit this switch, we get our light. And the beauty of it now is that the current, the load here, this light is the load. It's drawing 3 amps, but those 3 amps are not passing through this switch. The 3 amps are going through the relay here. The switch is just powering the coil inside of this relay, which is only a couple of milliamps. So we're not going to burn out this switch. Perfect. You could imagine how you would add more relays and continue to add on features. I also have this light here. This has a left turn signal, right turn signal, a brake light, and a running light. And you could imagine how all these would be connected through that relay. You would just have multiple relays controlling each individual light on this. And you'd have very little amps actually going through this. So that's like very, very, very basic circuitry that you would use in an e-bike. Now, one thing that you would want to add to this is a fuse block like this one for 2 reasons. One, it would greatly clean up the wiring. You would just have each parallel connection connected to one of these terminals here, and you would have all the grounds returning to here. You would have the main power supply positive going here, and the main negative going here. So it'll greatly improve your wiring and clean it up. And also, it's fused. So that means that, say for example, there's a short within this light. The light breaks and it short circuits and it's drawing a lot of amps. If you don't have a fused connection and it just draws as many amps as it pleases, it'll draw more than what this is rated for and it could kill this converter. However, if you have a fuse, and all a fuse is it's a very, very thin piece of wire. And so this is a 30 amp fuse, but if we looked at a 2 amp fuse, we would see an even thinner piece of wire in there. I know it's a little hard to tell, but it's very thin compared to this one. It's a very thin piece of wire that is designed to burn up at a certain point. So this one, when there's more than 2 amps passing through this, give or take, it'll get hot and then it'll eventually break and it'll open that connection so that there's no longer any power going to this circuit. We know this light draws 3 amps, so we would use something like a 5 amp fuse right before it. And then if this ever had some kind of internal short, that 5 amp fuse would pop, and then this light here, because this one is a little bit fancy, this light right here would light up, indicating that this fuse has popped. And we can go and check, is it because this light is broken? And now we just have a broken light, whereas if we didn't have the fuse, we could have potentially killed the DC converter or the relay as well. So I would say that's pretty much all you need to know. As you can see, this is what wiring in parallel looks like. If you wanted to add more relays, you would just wire another one in parallel. And if you wanted to add another load going through that relay, you would add another one in parallel. You just stack them up. Obviously, this ring terminal can only hold so much, and that's why you want to use a fuse block like this one. This one's from AliExpress. I think I got it for like $6, and it can handle up to 6 fuses, which is great. You're not really going to have more than that on an e-bike. You know what? Just a bonus. Let me show you how you would wire up this setup using this fuse block here. And by the way, the proper way to use these terminals is to use one of these Y terminals. When you have these crimped onto the wire, these just slide right under that screw, and then when you screw it down, it's nice and firm. In the next video where I'm doing all the proper connections, I'll do that. But for now, let's just go ahead and connect it like this. Additionally, the proper way to connect to one of these terminals is to use these spade connectors. They just slide right on and they're held in pretty well by friction. Sometimes your relays will also come with one of these holders that connect onto the relay. And then they break out into wires, and I guess the purpose of this is that if the relay ever breaks, instead of having to reconnect everything, you just slide it out and you pop in a new one. So I just did a 2 amp fuse going through the switch and the relay because, like I said, the relay only draws a couple milliamps. For this light, you would probably want to use something like a 5 amp fuse, but there's actually 2 lights and I'm going to wire them in parallel. So there's just a 10 amp fuse right there. And that's it. Light turns on, off, on, off. And now let's suppose one of these fuses pops. I'm just going to simulate that by pulling the fuse out. The circuit right there, it lights up red, indicating that the fuse has popped. There you go. And that's pretty much it. You're also going to need to know how to like crimp on certain connections and how to like put this all inside of an enclosure so that it could be mounted on a bike. And I'm going to cover that in the next video, but this was the very, very basics of electronics, enough to at least get you started playing around with relays and switches. And I was just demonstrating how to do it with a e-bike battery, but it's even better if you have a DC power supply like this and you can just supply voltage to the converter from here so that you don't have to have the battery with you. And these also have fuses built into them, so if you draw too many amps, it'll pop. And as well as that, it also has adjustable amperage here, so you can control what you want the max amps to be. And it tells you how many watts you're drawing. So this is just very nice to have when you're building a circuit like that, but not entirely necessary. You can do without it. So that's it for this video, guys. I hope you enjoyed, and if you have any questions, leave them in the comments below. I'll be sure to get to them. And if it'll be even better, because in the next video that I plan to make, I'll address those comments and answer it for anybody else who might have the same kind of question. Thank you very much for watching, and I'll see you in the next one. Peace.